Last time we looked at the benefits and drawbacks of radioactive decay. They can be dangerous, but we also have harnessed them to use them for some helpful things. Now we're going to look at how quickly that occurs and what happens when a nucleus is unstable, right? So we know it can decay. Atoms with an unstable nucleus undergo radioactive decay, which just means they release energy to become more stable. They might also release some particles. So here we have alpha decay, right? And some energy is coming out of this, and we get two different atoms we didn't start with. Now, on this is just a quick review, right? We can identify our decay by what particle comes out, or if it's just energy. This is alpha decay because a helium nucleus is an alpha particle. Now, how fast does this radioactive decay happen? Well, that's a little bit weird. It turns out that it depends on how much stuff is there, and it's a very mathematical probability thing. The more radioactive stuff you have, the quicker it decays. But any given atom may or may not decay at any given time. And so we actually talk about half-life, and it's the probability at which this stuff is going to decay. And it turns out that about half of the substance will decay every certain amount of time, and that's called its half-life. So for example, the beta plus decay of oxygen 15, if we started with a completely unstable sample, so all of the oxygen atoms in here are oxygen 15, they will change over time to a stable nitrogen 15 by going through beta plus decay. That's what this shows, right? So the oxygen changes into nitrogen when the proton emits a positron and changes to a neutron. This is stable. Once it gets to here, it'll stop changing. Not all decay chains are like that. Some decay chains will go through multiple steps before they finally reach a stable atom at the end. So everything starts and everything here is unstable. That means all of it is going to decay, but not all at the same time. Turns out about half of it will decay every 2 minutes. So that means if we had 100 samples of it, now 100 samples of oxygen 15 now changed into 50 samples of oxygen 15, but it's also 50 samples of nitrogen 15. Nitrogen 15, and that of course is 7 protons. So 2 minutes go by. That's what we call the half-life. That's how long it takes for half of the unstable atoms to decay. Now, if we continue, we only have 50 of the unstable things left. So 2 minutes go by, and of the 50 that we had, 25 of them will decay. And so now I'm going to have 25 oxygen 15 left, but now I have 75 of my nitrogen 15 left. And so you can see it wasn't 50 followed by the next 50. We started with 100, half of them decayed, that left us with 50, half of those decayed, now we're left with 25, half of those are going to decay, but we can't have half of one of them, so we're going to end up with like 12 and 13, right? So we go through another decay, and now we're down to 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of these that have not decayed yet, and then they'll go through another half-life, right? And we're down to 6 of these. Then we're going to go through another half-life. So every 2 minutes we cut what's left in half, and so now we're down to 3, and 2 minutes later we're down to 1, and finally it'll all become stable to nitrogen 15. But you'll notice that was a very gradual decay at the end, right? At the beginning, lots of it went away, and then some of it went away, and then some of it went away, and then some of it went away. This is an exponential decay, and it's doing this at a decreasing rate. So half-life tells us how long it takes for half of the sample to decay, but every time half of it decays, the next step, only half as much will decay. So if we were graphing this versus time, and we wanted to know how much unstable stuff was here, and we're just going to do this as a percent. If we started here at 100% at 0 time, then the first half-life, which we said was 2 minutes, would get us to 50%. And the second half-life, which we said was 4 minutes, would get us to 25%. And then the third half-life, which is 6 minutes for this oxygen, gets us down to 12.5%. And then the next one, 8 minutes, gets us down to 6.25%. And then the next one, 10 minutes, gets us down to 3.125%. And then 12 minutes gets us down to just over 1%. And then the last one, or whatever, gets us down to 0.6%. And so in a large sample of this, you may or may not get all the way to 0 because there's half. Eventually all of it will decay, but you can have 0.03%, right? So there's still going to be a few atoms that are unstable even after most of it has decayed. So 2 minutes 50%, 4 minutes 25%, 6 minutes 12%. I missed a little, right? But this curve is getting less steep as we go through time because there's less stuff to decay, but only half of it decays every half-life. So radioactive decay does not occur at a constant speed. It's faster at the beginning and slows down. It occurs in half-lives, so only half of the unstable matter decays every whatever half-life it is. And so a half-life is the amount of time it takes for half of a sample to decay, that is to change into smaller or less energetic things. So this is that whole thing drawn out in several steps here. And again, if this was a larger sample, you could still have a few of these particles that are unstable. So this table shows me the half-lives of several different radioactive things. Boron-17 is very, 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 very radioactive. And by that I mean its half-life is short, 0.005 seconds. As we go down this table, these things are becoming much more stable. And we can tell they're becoming much more stable because it takes longer for them to decay. On the top of this table, these are very unstable, and we can tell they're unstable because they decay very rapidly. Okay? So the longer the half-life, the slower it decays. Long half-life means it takes longer for half of it to decay, so it's slow to decay, and that makes it more stable. We can use this because we can actually calculate how much radioactive material is left in something and then figure out how long it's been decaying, and we can see how much time has passed. So if you've heard of carbon dating, carbon-14 is radioactive, and based on how much carbon-14 is left in something, we can determine about how old it is. Also used with potassium-40, 4.5 billion years, right? It's got a much longer half-life. So eventually there might not be any carbon-14 left, but the potassium-40 should still be around because its half-life is so much longer. So we do use half-lives to date things, tell how old they are.